This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at vector fields. Computer. That should be compute. Okay. Now we're going to compute the magnitude and then sketch several representative vectors in the vector field. Let me get over here. We have f of xy equals yi plus 2xj. Now our magnitude is going to be the square root of y squared plus 2x squared, which is going to give us y squared plus 4x squared. Now there's different ways you can sketch the several representative vectors in the vector field. You could set this equal to c, like that, and then you could get rid of the square root if you wanted to by squaring both sides. And then you could try plugging in different values for c. Plug in 2, 3, 4, so forth. For example, if I plugged in 2, we'd have y squared plus 4x squared is equal to 2 squared. Or we'd have y squared plus 4x squared is equal to 4. And if I were to divide everything by 4, then we'd get y squared over 4 plus x squared over 1 is equal to 1. Now this shape right here is an ellipse, where your x is a distance of 1 and your y you got a distance of 2. So that's what that shape would look like. Which means I could plug in, this would be a good representative point, 1, 0. This one would be 0, 2. And this one would be negative 1, 0. And then this one down here would be 0, negative 2. Okay. So if I come over here, scroll up here. This is for c is equal to 2. And 0, 2. One 0, negative 1, 0. And 0, negative 2. Well, if we were to find f for these, this is x and this is y, of course, so we'll plug these in. For this one, if I put 2 in for y, I get 2i. If I put 0 in for x, I get 2 times 0, 0 times j drops away. Now for this one, if I plug that in for x and that in for y, the y would drop away. 1 in for x, I get 2j. And if I plug in negative 1 and 0, this drops away, and we got 2 times negative 1, which is negative 2, so that's negative 2j. And plug this in for x and this in for y, and we're going to get negative 2i. Okay. Now if I plugged in something else here, c is equal to 1 might not be too bad. Let me think if that's a true statement. Wouldn't work out perfect, but c is equal to 4. Let's try that. Okay, so we're going to have y squared plus 4x squared is equal to 4 squared, which is y squared plus 4x squared equals 16. We'll go through and divide everything by 16. So we've got y squared over 16 plus x squared over 4 equals 1. And again, this is an ellipse. X will be out here. Y will be up 4. It's always the square root of the denominator. And this would be a good point to go with. Okay, so we're going to have 0, 4, and 0, negative 4. And we'll also have 2, 0, negative 2, 0. Now again, we're going to put each one of those into our vector to find out what f is. So this is x and this is y, so that would give us 4i. So this one's f is equal to 4i. This one will be f is equal to negative 4i. Put this in for x and this in for y. The y drops away. And we've got 2 times 2, which is 4, so that'd be 4j. And put negative 2 in there, and we get f is equal to negative 4j. Okay, so let's sketch these now. And that's probably good enough. I don't want to do any more than that. I think you get the idea. 0, 2. And then 1, 2, 3, 4. 1, 2, 3, 4. 0, 2 would be right there. And that particular one is 2i. So it's going to go 2 to the right. So it'd look like that. Our next one, 1, 0. It was 0, 0, 2, yeah. 1, 0. Which is right there. And that's 2j. So that's going to go up 2. And then our other one is negative 1, 0. And it's going down 2. It was a negative 2j. And then this is 0, negative 2. 0, negative 2. And it's negative 2i, so it's going 2 this way. Okay, so let's do these points then. We got 0, 4, which is right here. And it was 4i. So it's going to go 4 to the right. Like that. We had 0, negative 4. Right there. And it's going negative 4i, so it's going negative 4 to the left. Or it's going 4 to the left. That should be a straight line. 2, 0. This one right here, and it's going 4j. So it's gone up 4. And then negative 2, 0, and I'm assuming it's going down 4. Yeah. So it's going down 4. Now those are just a few representations of our vectors. Now I might want to do some over here to see what's happening. You can see this over here follows a certain pattern, but what's it doing here? But that's good enough for what we're doing here. So let me go ahead and save this. Vector fields. I find these kind of tedious to draw. Vector fields page01.pdf. Okay. Next thing we want to do is we want to find a conservative vector field for the potential function by finding its gradient. So we got f of xy is equal to x to the third plus 4y squared. Now a hint, when you got this right here, you see we're going to take partial with respect to x plus partial with respect to y, and that's going to give us our answer. Well, if I take the partial with respect to x, that would give us 3x squared. Partial with respect to y will give us 8y. And then we're trying to find the conservative vector field, trying to find f. And that's going to be equal to a partial with respect to x, which was 3x squared, I, plus the partial with respect to y, j. So this will be 8y, j. And that's our answer. Let's take a look at this one. We got f of x, y, z is equal to e to the 3x minus e to the y squared z to the third. Same instructions. And I got 2 dimensions here, but the third dimension we have to find our partial with respect to x, y, and z. So let's find our partial with respect to x first. This second e doesn't have any x in it, so that drops away. And derivative of e to the 3x is e to the 3x times the derivative of the exponent, which is 3. So that's going to give us 3e to the 3x. Now our partial with respect to y. This part drops away, and we got minus, or negative. The derivative of e to whatever power is e to whatever power. That doesn't change. But then you have to multiply times the derivative of the exponent with respect to y. So that becomes 2yz. Now the z just is a constant, so we just carry it down. We treat it as a constant. So this gives us negative 2yz e to the y squared z. Now we also need a partial with respect to z. The first e doesn't have a z in it, so it drops away. And again, this becomes negative e to the y squared z to the third. I forgot to put through third here. I's are bad. Times the derivative of the exponent with respect to z. So that gives us 3y squared z squared. Let me come up here and double check this. Okay, partial with respect to y. 2y z to the third. Okay, so then that'll be z to the third there. Okay, partial with respect to z. Yeah. Okay, so that gives us negative 3y squared z squared e to the y squared z to the third. So now I think they're asking for that. Yeah. So our vector field, conservative vector field, we'll take partial with respect to x, which is 3 e to the 3x, I. Partial with respect to y, which is negative 2y z to the third, e to the y squared, z, j. And then the partial with respect to z, so we've got minus 3 y squared, z squared, e to the y squared, z to the third, k. Assuming I didn't make any other mistakes in there, that's our answer. Let me double check it real quick here. Okay, 3 there. Our partial with respect to y is negative 2y z to the third, e to the y squared z. That should be a third power there. There we go. Boy, I better go back to sleep. Okay. Partial with respect to z. I actually find if I don't show all the steps, it actually comes out easier. There we go. That's correct now, hopefully. Okay. Now the next problem asks us to verify that the vector field is conservative. Number 4. And we got f of xy is equal to x squared y I plus 1/3 x to the third j. Now first off, what's before our I is m, and what's before our j is n. And a hint here is if you take the partial of m with respect to y, and this isn't the equals, we're wondering if it's equal to the partial of n with respect to x. Okay, well the derivative of m with respect to y would give us x squared. And again, this is a question mark at this point. Partial of n with respect to x. Take 3, put it out in front, so we got 1/3 times 3x squared. 1/3 and the 3 cancels, and we got x squared is equal to x squared. So the question here, verify it's conservative. We just did by getting those equal to each other. Let's take a look at another one of those. Got f of xy is equal to 7xy I plus 7/2 x squared j. Now again, what's before our I is our m, and what's before our j is our n. And we want to take the partial of m with respect to y, and we're wondering if that's equal to the partial of n with respect to x. Well, the derivative of m with respect to y gives us 7x. Partial of n with respect to x, take your power, put it on front, lower it by 1. So we get 7x, and then these 2's cancel, and we got 7x over here. Since both sides equal to each other, then that verifies that actually this one's determined whether it's conservative. So here the answer would be yes, since they're equal to each other. Let's look at one more. We've got f of xy is equal to 2x squared y I plus x squared y to the third j. Same instructions. So this is m and this is n, and we're wondering if the partial of m with respect to y, y, is equal to the partial of n with respect to x. Well, okay. Well, the derivative of m with respect to y would give us 2x squared partial of n with respect to x would give us 2x y to the third. I can see they're not going to equal each other, are they? So this will be no. These are not, well, this vector field is not conservative. I don't have room here, so let me go ahead and save that page. Let's look at this one. You got f is equal to 2yi plus 2xj. Instructions are: determine whether the vector field is conservative. If it is, find a potential function for the vector field. Well, first off, this is our m, and this is our n. So we need to take the partial of m with respect to y, and we're checking to see if that's equal to the partial of n with respect to x. Well, the derivative of m with respect to y is 2, and the derivative of n with respect to x is 2. So it is conservative, which means we can find we can go further and find the potential function. That's what they're asking you here. Find a potential function. Well, besides this being m and n, they're actually, this right here is a partial with respect to x. So what they're telling us is they're telling us a partial with respect to x is equal to 2y. And they're telling us the partial with respect to y is equal to 2x. And I have this over in this slide here. You can see that what's before I is the partial with respect to x, what's before your j is partial with respect to y. Well, to go backwards then, to find our function, we're going to take the integral of 2y with respect to y. Try it again, respect to x. It'll always match whatever we got right here. We also need to do this one. So this will be the integral of 2x with respect to y. Well, we're integrating with respect to x, and there is no x, so this just becomes 2xy plus k, constant. And this one, the integral with respect to y, there is no y, so this just becomes 2xy plus k. Now our potential function, what you do is you merge these together. And if they both have the same thing, you don't write it down twice. See how they both have a 2xy? So we'll just put a 2xy once, and then plus k. And that's our answer. Let's take a look at this one. Okay, so we got f, and is equal to 3x squared y I plus x to the third j. Again, this is m, and this is n. It's also, this here is the partial with respect to x, and this is the partial with respect to y. We'll come back to that. First thing we need to do is verify they're conservative. So we're going to take the partial of m with respect to y, and we're wondering if that's equal to partial of n with respect to x. The derivative of m with respect to y would give us 3x squared, and the partial derivative of n with respect to x would give us 3x squared. So they're conservative. Well, we said that the partial with respect to x is equal to 3x squared y, and partial with respect to y is equal to x to the third. So for our potential function, going backwards, we'll take the integral of 3x squared y with respect to x. And we're also going to take the integral of x to the third with respect to y. Again, If this is x here, you have to have an x here. If this is a y here, you have to have a y here. Okay. Well, integral this with respect to x. We got x squared, so you add 1 to your power divided by your new power. So we're going to have 3 times x to the third over 3y plus k. 3's cancel, and we got x to the third y plus k. Now over here, we're integrating with respect to y, so there is no y, so we just got x to the third y plus k. So our potential function, we merge these together. Again, if they have any items that are the same, we don't repeat it. So we'll just write down x to the third y once plus k. And that's our answer. And got another one here. Let's take a look at this. Got f equals 3e to the x y I plus x to the third j. This is our m and this is our n. So we're going to take the partial of m with respect to y, and we're wondering if that's equal to the partial of n with respect to x. Well, the derivative with respect to y would give us 3e to the x, and this one over here, the derivative with respect to x, would give us 3x squared. They don't equal each other, do they? So this is not conservative, and we don't go any further on that. If it's not conservative, then you don't go on and try to find your potential function. Let me actually save this and bring up a new page. A lot of these we're looking at are related to physics, and we're not going into a lot of detail on that because physics is not my specialty. Okay, this says find the curl F for the vector field at the given point. Okay, so F is going to equal to x squared yi. That y shouldn't be bold. That's not a vector. Minus 3x yz j plus 4x z k. Okay. Now there's three items here. Our curl is equal to this, this, and this. Well, the third one is probably going to be your most beneficial one to use, at least in these problems, because we're given m and n and p, and so it's easy to work with. M is what's before I, n is what's before your j, and p is what's before your k. So our curl F is going to equal the partial of p with respect to y minus the partial of n with respect to z I minus partial of p with respect to x minus partial of m with respect to z, j, plus partial of p with respect to, okay, I'm lying. Partial of n with respect to x minus partial of m with respect to y, k. Let me double check all that. Py nz, py nz, px mz, px mz, nx my, nx my. Okay, that's all correct. Okay, so the partial of p with respect to y. Well, there is no y here, so the derivative of that would be 0 minus the partial of n with respect to z. Well, here we've got a z, and derivative of z is 1, so that drops away, so we get left with negative 3xy. And that'd be I. Okay, minus partial of p with respect to x. Well, the derivative of x is 1, so that leaves us 4z. Minus partial of m with respect to z. There's no z there, so that's 0. J. Plus the partial of n with respect to x. That gives us negative 3yz. Minus partial of m with respect to y, which would give us x squared. Okay. And we double check all that now. Partial of p with respect to y is 0. Minus partial of n with respect to z would be negative 3xy. So that's negative negative gives us 3xy. I. Okay. Partial of p with respect to x would give us 4z. Yeah. Minus partial of m with respect to z. There is no z, so that's 0. So here we got negative 4z j. Partial of n with respect to x would give us negative 3yz. Minus partial of n with respect to y give us x squared. So this gives us negative 3yz minus x squared k. And that's our answer. Okay. Now this one is a test for a conservative vector field in space in 3 dimensions. Suppose the m, n, and p have continuous first partial derivatives in an open sphere Q in space. The vector field given by f of x, y, z is equal to mi plus nj plus pk. And f, I, and j and k are vectors. I just forgot to bold them. Is conservative if and only if the curl is equal to 0. That is, f is conservative if and only if these are true. So let's go ahead and work a problem. We'll flip back to that. Okay, so f is equal to x squared, y to the third, z to the third, I, plus x to the third, y squared, z to the third, j, plus x to the third, y to the third, z squared, k. Double check that. X to the third. Okay, 2, 3, 3, 3, 2, 3, 3, 3, 2. Okay, that looks right. Well, let's work on this. First off, let's identify. This is m, this is n, and this is p. First thing we got to check is the partial of p with respect to y, and we're wondering if that's equal to the partial of n with respect to z. So let's check this. Partial of p with respect to y. Again, we're taking derivative of y to the third, and all the rest just carries along. So that's going to give us 3x to the third, y squared, z squared. Partial of n with respect to z. Again, the x to the third, y squared just remain. We're just taking derivative of z to the third. So that gives us 3x to the third, y squared, z squared. And they match. So that one checks. Well, now then we need to check partial of p with respect to x. And we're wondering if that's equal to partial of m with respect to z. Partial of p with respect to x. Again, the y to the third, z squared just remain. We're taking derivative of x to the third. So that's going to give us 3x squared, y to the third, z squared. partial of m with respect to z. The x squared y to the third remain, just take derivative of z to the third. So that's going to give us 3x squared y to the third z squared. And that checks. And then our last one here, partial of n with respect to x is equal to partial of m with respect to y. Partial of n with respect to x. That gives us 3x squared y squared z to the third. Partial of m with respect to y would give us 3x squared y squared z to the third. And those match. So yes, it is conservative. Now the second part of this says after you determine whether it's conservative or not, then find a potential function for the vector field. Well, first off, note that our partial with respect to x is equal to x squared y to the third z to the third. Our partial with respect to y is going to equal to x to the third y squared z to the third. And our partial with respect to z is going to equal to x to the third y to the third z squared. So again, partial with respect to x matches what's before your I, partial with respect to y matches what's in front of your j, and partial with respect to z matches what's in front of your k. To go backwards. Well, on this one, we're going to take the integral x squared y to the third z to the third with respect to x. This one, we'll take the integral of x to the third y squared z to the third with respect to y. And on this one, we'll take the integral of x to the third y to the third z squared with respect to z. Well, the other variables are just constants, they just remain. So the integral of x squared gives us 1/3 x to the third y to the third z to the third. And before we put k here, but now we'd put a function. Oh, I don't know, g of yz. Try to remember the notation they use in the book. But then here I'll take the integral with respect to y. Again, the y squared, you add 1 to your power divided by new power. So that gives us 1/3 x to the third y to the third z to the third plus h of the other two variables. This is y, so x, z. And then this one gives us 1/3 x to the third z to x to the third y to the third. Boy, I'm out of it here. Plus, I don't know, I is probably bad since we're let's see, I, J, K, L, maybe? L of x, y. So our potential function here is going to equal to 1/3 x to the third y to the third z to the third plus our constant. There is no other functions. What you do is you merge these three together, and what they have alike you don't repeat. They all three have this, so I don't repeat it. Now if these two had it, but this one didn't, but it had something different, then you'd put down this once and then you put that one down. That's what it means by the function. So that'd be your answer. Okay. Now, definition of divergence of a vector field goes like this. Divergence in 2 dimensions is just a partial of m with respect to x plus a partial of n with respect to y. The divergence in 3 dimensions is partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z. If the divergence of f is equal to 0, then f is said to be divergence free. And that means a lot more if you're in physics. But let's find the divergence here. So our vector field going to equal to x to the third I plus 4e to the y j. It says find divergence. Well, this is from our formula. Remember, what's in front of our I is m, what's in front of our j is n, and we want the partial of m with respect to x. So our divergence, partial of m with respect to x, plus a partial of n with respect to y. Well, partial of m with respect to x gives us 3x squared, plus partial of n with respect to y. Well, the derivative of e to the y is e to the y, so that gives us 4e to the y. And that's our answer. Let's take a look at this one. Our vector field, we've got 3 dimensions here, is equal to a natural log of x squared plus y I plus x squared y to the third j plus natural log of 2y squared minus z squared k. Okay, so this will be m, this will be n, and this will be p. And our divergence of f is going to equal to the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. Well, the derivative of natural log of something is 1 over whatever. So we've got 1 over x squared plus y, what's inside of parentheses. But then you have to multiply it times the derivative of what's inside of parentheses with respect to x, because that's what our partial is. So that'd give us 2x. Plus partial of n with respect to y. Again, the x squared just remains. The derivative of y to the third, that gives us 3x squared y squared. Plus, then the partial with respect to z. Well, the derivative of natural log of something is 1 over whatever's inside the parentheses, 2y squared minus z squared, times the derivative of what's inside the parentheses, the partial derivative, with respect to z. The 2y squared drops away, and that gives us negative 2z. So this becomes 2x over x squared plus y plus 3x squared y squared minus 2z over 2y squared minus z squared. And that's our answer. Let me go ahead and save that. And let's look at our next problem. This is finding divergence of the vector field at the given point. So we got f is equal to x squared y z to the third I plus x squared minus y squared j plus z to the fourth k at the point 3, 1, 1. Now remember, these vector fields are all over the place. When the first graph we did, we just showed a few, but these may represent, I'm just guessing because I've never taken those engineering physics classes, but they may represent maybe gravity. You know, gravity's everywhere, but maybe it's different at certain spots. Magnets. Some places it's stronger, and some places it causes to do this, repel, you know. So it's everywhere. But we're specifically finding it at this point. Okay, well this is M, this is N, and this is P. And our divergence of F, and it's going to equal the partial of M with respect to X, plus a partial of N with respect to Y, plus a partial of P with respect to Z. Okay, so partial of M with respect to X, the Y Z to the third remain, and derivative of X squared is 2X. So we got 2X, Y, Z to the third. Plus, partial of N with respect to Y. The X squared drops away, and that becomes a negative 2Y. Take derivative. Then the partial of P with respect to Z. So that becomes plus 4Z to the third. Okay. Now they're wanting us to plug in the point. So we're going to plug in 3, 1, 1 for X, Y, and Z. Again, that's X, that's Y, and that's Z. So we're going to have 2 times 3 times 1 times 1 to the third minus 2 times Y, which is 1, plus 4 times Z to the third. Z was 1. 1 to the third is 1 times 1 is 1. 2 times 3 is 6. So that's 6 minus 2 plus 4, which gives us 8. And that'd be our answer. I'm going to go ahead and save that. And that's the end of that section. So vector fields.